So yesterday we started out talking about mass, weight, and apparent weight, and we said that mass is something that's measured in kilograms, and weight is actually the force of gravity on your mass. And so your weight can change kind of depending on the planet that you're on and the gravity of that planet. And so weight is mass times gravity of wherever you're at. And usually we're going to be on Earth, and it's in that case 9.8 meters per second squared. But this carries a unit of kilogram meter per second squared, which we're going to call a Newton. Now your apparent weight we talked about really briefly yesterday, but your apparent weight is really just a feeling, right? And so, excuse my handwriting, I'm writing with my finger. Your apparent weight is a feeling that you feel. It's a perception, it's not a reality, and it's usually a perception because of changing accelerations or changing differences in the normal force that's being applied to you. And so every single day we have contact forces, and particularly normal forces from the ground that act on us, and we're so used to them that we don't even think about it. And so we have this kind of perceived built-in notion of our weight. But when you get in something that is moving, right, like an elevator or a roller coaster or even a car, as that object accelerates, we feel different, right? We can feel heavier or we can feel lighter. These little equivalencies down here are going to be useful for you coming up. And so knowing how to convert between pounds and kilograms, which are both measures of mass, and so I should probably add that up here. In the customary system, we use pounds, and so if you have a problem in pounds, you need to convert that to kilograms, which is the metric standard for mass. But then if we need to convert then those kilograms to newtons, I can do this equation, or I can just use that conversion factor. Either way works. Doesn't matter to me what you do. So let's talk about your apparent weight. This is a really fun ride at an amusement park. And so if you've never been on one of these rides, basically what they do is they start you at the bottom, way down here, and they accelerate you towards the top, right? And a lot of them will go really fast towards the top. And so I want you to think for a second, even if you've never been on one of these rides, if something is going really fast upward, does it increase what you feel is your weight, or does it decrease what you feel is your weight? Do you feel lighter as a result of that? Well, and so you should know that, right, if this is accelerating upwards against gravity, then you not only have gravity pulling you down, you've now got that seat pushing up on you. And so that's going to make you feel a lot heavier, right? And so when you do these apparent weight problems, always think about the direction that things are going and what you should feel, right? That's your reasonability check. So they zoom you up to the top, and you feel much heavier than normal. And then they stop you at the top. And then there's this long pause and this long wait before they completely drop you. And when they do drop you, right, that seat almost falls out from under you, and your body has to work to catch up. And so if that seat is falling out from under you continuously, then it's not applying a heavy normal force. And if you don't feel that normal force that your body has grown accustomed to in its 20 years on Earth, then you feel lighter, right? And that's your apparent weight. Formula worth writing down, that your apparent weight is your actual weight, right? Mass times gravity, plus your mass times the acceleration of whatever it is that you're in, right? And so, again, weight apparent, yes, it's going to be a force, but it's going to be a perceived force, right? It's not an actual one. And that's the big distinction we want to make. And so let's imagine that we're in this ride, right? And let's say we weigh 70 kilograms. You all pretty much do. How fast would this ride have to accelerate downwards to make a 70 kilogram person feel weightless? And so I've really only given you two pieces of information in this problem, right? There's a 70 kilogram person, and they feel weightless. And so, well, let's figure that out. All right? I'm going to use this weight apparent formula, and I'm actually going to go ahead and expand it. So weight apparent is equal to my regular weight is mass times gravity plus mass and then my acceleration on the y due to whatever machine that I'm in. And so I'm asking how fast this ride has to accelerate. That tells me that I'm looking for that. Okay. And so I'm going to go ahead and kind of rearrange this formula before I even start plugging in numbers. And so my weight apparent is going to have to be, I'm just going to put this little a. I've got to subtract mg, my normal weight, from both sides, mg. So I will subtract mg, and then I'm left with m over ay. Okay. And then I've got to divide both sides by m. Okay. M. And so I wind up with, let's go ahead and erase everything on the side. So I wind up with my weight apparent minus my weight divided by mass is going to equal my acceleration along the y. Okay, so now I can start plugging in numbers. This person is going to feel weightless. So what variable is that going to be? Well, it's going to be my weight apparent, right? It's a feeling. So I'll plug that in for weight apparent. It'll be 0, right? Minus. And then my actual weight, right? And so this is going to be 70 times 9.8. And then divided by the mass of that person, which is going to, again, be 70, right? And whatever that is going to equal my acceleration on the y-axis. I'll give you a second to do those calculations. All right, and so when I do that, that 70 kilograms times 9.8, which is our gravity on Earth, I get negative 686, right? And I'm going to divide that by my mass, and lo and behold, 686 divided by 70 is negative 9.8 is my acceleration on the y. And so this device is going to have to enter free fall in order for me to feel weightless. And that makes sense, right? If it's falling with the same acceleration that I would fall, then there is no normal force pushing on my behind, and I feel weightless. All right. I'm going to give you a minute to do your weight on other planets, right? You can convert your mass in pounds to kilograms, and so we can use those conversions that I talked about before, right? Where are they? These guys down here. And I know that 1 pound equals 4.45 newtons or 4.454 kilograms, right? And so for every pound, I'm 0.454 kilograms. So if I'm 120 pounds, then I'm going to multiply that by 0.454 kilograms. And when I do that, you can do your own, right? Times 120 times 0.454. Then I'm going to be about 54.5 kilograms, right? And so if I'm a 120 pound person, this is my mass in kilograms. So then if I want to figure out what I weigh on other planets, right? Well, weight is mass times gravity. And what I've given you here is the gravitational acceleration on all these different planets. And so you're going to just take your mouse and choose any 3 planets. So we kind of did this yesterday. But then the nice thing is that whatever weight you get on that planet in newtons, you can then convert back to pounds. And so that gives you something easy to think about. Like, oh, okay, you know, if I'm 10 newtons on this planet, well, what does that feel like in pounds? And you can kind of compare. So I'm going to choose Jupiter. I'm going to choose Pluto, right, because they're extreme. And I wonder, I don't know, maybe I'll choose Venus, right? Because that's pretty close to Earth's acceleration. And so what I'll do is take my mass in kilograms and times it by all of these. So times 54.5 times 54.5. And you can go ahead and do this for yours, times 54.5, right? And I'll get some mass in newtons. Or I'm sorry, some weight in newtons for what I weigh on that planet. Pretty fun little exercise, right? Space travel is a good time. All right, and then again, to give you an idea of where planets are, if you don't remember from elementary school, I'm going to give you this. Right? This is the relative sizes of the planets, and I've also given you the masses of the planets, so you can kind of take a look at, okay, well, why is Jupiter's acceleration constant bigger? Well, because Jupiter is a heck of a lot more massive than Earth. Right? And let's see, Venus is the closest mass I've got on here to Earth. And so the gravitational constant of a planet actually depends on the mass of that planet. And we'll get to that in a few chapters, but that's a little sneak preview. And so we talked about your homework, and I will do a little YouTube video where I solve a couple of these, and I'll send that to you at some point this weekend. But for today, I want to go on to normal forces. And so normal forces, we kind of did this exercise when I had you guys stand up and push on a table, and you had a little tiny push, and you had a really big forceful push with your whole hand. And what we found is that the table pushed back equal and opposite. And so when you pushed a little teeny tiny force, well, the table pushed back a little teeny tiny force. And when you push back a big force, the table pushed back a big force. And so kind of the key to these is that normal forces can actually adjust to the balance of the force. Okay? We also know that normal forces are perpendicular to the surface. And so if I've got a person who's walking on the ground, then the normal force is pointing straight upwards, and that's not a good arrow for straight upwards, so I'll put the perpendicular symbol. If I've got some person who is, for whatever reason, pushing on a wall, right, then the normal force, that wall is pointing straight back out at them, and it's perpendicular to the surface of where the force is being applied. Right, and so there's all kinds of things. I mean, I could have somebody pushing on a ceiling, trying to raise the roof, and that normal force is going to point down. So normal forces really just kind of depend on the situation, right? And they can adjust, and we need to always take that into consideration. This is interesting on an incline because, well, we've worked with inclines before, and one of the important things to remember is that even though I've got an incline, right, I am tilting kind of my perceived axes to go with that incline because it makes my problem solving a lot easier. And so we're still doing that, right? And now, instead of just working with acceleration, well, we've got to figure out these normal forces too on an incline. And that's okay. You can use a lot of the same math that you used before. This is a really brief, just little kind of explanation here for you. These pictures of how to analyze force in an incline are, where are they? Are on page 143 for you. And so if I've got, simplified this snowboarder on an incline, and I'm calling the hill my x-axis, even though, like, the Earth is down here, I'm going to represent my snowboarder as a circle because they're easy to draw. The normal force of the hill and the snowboarder is going to be perpendicular to the hill. And so it'll be straight up on my y-axis, and that's fine, right? That part's easy. But where does the weight of this person point? Well, it actually points straight down towards the ground, right? And so this, and particularly the weight, is not along this x and y axis that I have drawn. And so I'm going to have to figure out the x and the y components of it. And this is a really kind of your quick problem solving, right? And so the y component of it is negative weight, right? Or the magnitude of the weight with the direction. And then if I want to find the x component, I'll do this little calculation here. And so these are great things to add to your formula sheet. And if you want to add the whole drawing, you can absolutely do that. I don't want you to get held back on not knowing geometry, like alternate interior angles are equal. You can always use this drawing to help you out with the x and y components of weight on an incline, so that you can break them down and add the vectors of the forces. And so once I figure out weight, right, as an x component and a y component, well then if there's any other forces like kinetic friction, right, I can just add the kinetic friction in the x component of the weight, and I can add the y component of the weight and the y component of the normal force to figure out, okay, well, where's my net force and where is this thing going to go? All right. Very quickly, I told you guys that static and kinetic friction always work in the opposite direction of motion. I'm also going to introduce this thing called rolling friction, and that's going to be represented with an F sub R. And so we've got static, kinetic, and rolling friction, and now we're going to start applying numbers to these, right? These are the equations to calculate the frictional force of all of these kinds. Do remember that static is just that. Static means not moving, and so if I've got somebody pushing on something that's not moving yet, okay, then I'm looking at static friction. So let's say my person is pushing that way, then static friction will be working to oppose that motion. Once that object gets moving, then it becomes kinetic friction or rolling friction, depending on the situation. So if I've got a big refrigerator, I'll use kinetic friction, but if I've got like a tire on concrete, I'll use rolling friction, right? It's just a really easy contextual clue. If it's rolling, use rolling friction. If it's not rolling and I'm just kind of like pushing or sliding, use kinetic friction. And so these formulas have this kind of new variable that we've talked about. These subscripts tell me what kind of friction I'm dealing with, so static, kinetic, and rolling friction. But now they've got these little like U's, and we haven't seen that before. And so what we do is we call this the coefficient of friction. And a coefficient is just like a constant value that I put before something in order to do a calculation correctly. You won't know what the coefficient of kinetic friction is unless it is explicitly told to you. It's not something you find, it's not something you know intuitively, and it depends on the object, and you know this, right? That it's a lot easier. Let's say I have something moving on ice and something moving on, I don't know, carpet or gravel or something. It's going to be a lot easier to get that thing moving on ice than it is on gravel, and that's because of this kind of coefficient of kinetic or static friction. It's just easier on some surfaces, and so it changes depending on the situation. On page 144 in your book, right, you've got a beautiful table that's going to let you know what those coefficients are. Sometimes they will tell you, in a word problem, like I'm sliding a wood box on a wood floor. The box isn't moving yet, and so then I think, okay, that's static, and I'm going to be using 0.5 for the coefficient of static friction, right? If I'm sliding a wood box on a wood floor, but it is moving, then I'm looking at kinetic, and I need to be using this. And so this table is going to come in really handy. If you want to have it on a formula sheet, that's great. That's easy access in your problem solving, and you won't have to keep flipping back and forth. Oh, really quick question too. I'm sorry. So what do you think a high coefficient of kinetic friction means? And so if this number is high, what is that going to do to the actual frictional force? And so as the U increases, what happens to the frictional force? Well, it's going to go up, and you can play with numbers here, and you can pretend, okay, so if I've got frictional force of something, and it's got a static coefficient of 2, right, times the normal force, and then if I increase that coefficient because I'm changing surfaces, and it increases to 4 times the normal force, well, the normal force is the same, right? It's just that equal and opposite push based on the situation. But if I change surfaces and increase the coefficient of friction, well, my frictional force is going to go up. And so always, always, always draw your pictures, and always, always, always use this table. All right. Drag, you guys have been wanting to do this all along. A lot of times we've told you that drag is negligible. Right? And this negligible means it equals 0. It means ignore it. But now I'm giving you a formula to calculate drag. And so before we totally get to that, I want to ask you who falls faster. And so I'm going to draw this little situation for you. And so who falls faster, right? If I have a box that I'm dropping from a helicopter, right, like supplies to an area, let's say nothing in there is fragile, and I just need it to get to the ground really fast, and I've got these parachutes attached, right, so that it doesn't totally splatter. And one of these has a really big parachute, and the other one has a little tiny parachute. Which one is going to fall faster? Well, easily, right, this one, because it's not going to have as much air resistance. With a smaller parachute, there's going to be a smaller force pushing upwards, as opposed to this situation where this parachute is kind of catching a lot of air. It's got a lot of drag, and so it's going to have a really big force pushing up to counteract the weight of that object coming down. Right, and so those forces will be a little bit different. If I want to get the drag of an object, I can calculate that, and we're using the variable capital D for drag, as 1/4, and then this is our drag coefficient. It's always the same for every single problem, and so this new little kind of Greek P that you're looking at. A stands for the cross-sectional area of the object, and so if I'm dropping the box, right, then I'm going to look at, okay, well, if I look at the bottom of the box, what is that cross-sectional area? And so for a box, right, the area is the length times the height, or length times width, whatever formula you learned. If I'm dropping like a cylindrical object, then I'm going to look at the cross-sectional area that air surface is hitting. And so for this one, it would be a circle, and the area formula for a circle is pi r squared. Right? If I have something funny like a rocket, or some kind of irregular shape, just generalized in your basic geometries, right? Okay. So am I looking at a triangle or a circle or a square? And then v is the velocity with which that thing is falling. And so the velocity is going to depend on kind of the moment of the fall. And you'll have to read carefully for that. But your drag formula, another good one for your formula sheet. And if you want to start listing variables, because this is getting to be a lot of variables and you don't know what they mean when you just look at this basic formula, then do that on your formula sheet as well. Again, it's preventing the back and forth flipping. All right. And Alright, and last but not least, your homework for this weekend. You do have a few conceptual problems, some multiple choice, and some calculation problems. Use all the tools at your disposal, and know that we have not left behind constant acceleration and constant velocity formulas. And so if you have an old formula sheet, just keep adding to it, because sometimes you will need to go back to it. I'm going to do a few homework calculation problems, and I'll send those out tomorrow in a YouTube video. But other than that, happy solving. And you all have each other's phone numbers, so call each other when you have problems. You do have a homework quiz that will open up tomorrow, Friday, and it is due by Sunday at midnight or 11:59 p.m. To be sure. There is no lab this weekend, right? We just had that getting to know you exercise. You all got a grade. Great job. You made 100. Good luck on your homework quiz, and please email me if you have questions. I'll be checking. Bye.